3i Atlas is moving closer to the sun. There's still so much we don't know.
There's a mysterious interstellar object hurtling towards our solar system, exciting scientists across the globe.
Atlas swept past Mars in early October 2025, blazing through the red planet's neighborhood with a velocity and trajectory that both exhilarated and mystified planetary scientists. That passing marked not just a fleeting celestial cameo, but a rare moment when interstellar origins collided with the familiar environment of our solar system's inner planets. The encounter itself and what transpired in that brief window sent ripples through NASA's gaze and beyond, because the observations and surprises that followed forced a reckoning with how much we really know about such visitors. Before we start, hit the like and subscribe buttons for more exclusive news. This interstellar traveler was first identified in July 2025 by the Atlas Survey Telescope, and from day one it defied expectations. It was clear immediately that 3i Atlas was not bound by the sun's gravity. Its orbit was hyperbolic, meaning it came in from beyond and would head back out, never to return. In that sense, it belonged wholly to the realm of wanderers, objects cast off from distant stellar systems. But unlike the two interstellar objects before it, Oumuamua and 2I/Borisov, this one already showed signs of being more active, more dynamic, and more enigmatic. As 3i Atlas approached the inner solar system, telescopes across Earth and space strained toward it. Its rise in brightness, its coma and tail, the spectroscopic signatures of its gases, all of those became immediate priorities. It already appeared to be shedding material, indicating cometary behavior. But the details of that behavior diverged from what standard comet models would predict. It was already showing a coma while still well outside the orbit of Jupiter, in a region where solar heating is usually too weak to drive substantial sublimation. That in itself was odd. The decision to watch 3i Atlas closely became all the more compelling as it neared Mars. The red planet occupies a vantage point freed from Earth's glare for part of the approach, and a fleet of Mars orbiters and rovers stood by, capable of turning their instruments to catch the visitor. The European Space Agency's spacecraft around Mars, including Mars Express and the ExoMars Trace Gas Orbiter, were among those positioned for imaging and spectroscopic study during the flyby window. Some Mars assets had ultraviolet imaging capabilities such as MAVEN's IUVS, and instruments on other spacecraft like the Emirates Mars Hope probe were capable of picking up signals in relevant wavelengths. Mars rovers might even pick up faint signatures from the surface during favorable conditions. When 3i Atlas reached its closest approach to Mars, it came within tens of millions of kilometers, a cosmic near-miss. That proximity allowed an unprecedented geometric vantage. Instruments orbiting Mars could observe the comet from angles Earth-based telescopes could not, offering a unique set of parallax baselines, alternative solar phase angles, and access to the ultraviolet regime with fewer interference constraints. Throughout the period from October 1st to October 7th, the various Mars orbiters coordinated their efforts to track the comet's passage. In that interval, at its closest, the distance between the comet and some spacecraft dipped to around 30 million kilometers. The imagery and data collected during that window opened fresh layers of insight. The structure of the comet's coma, how gas and dust were ejected, and how solar radiation pressure and outgassing forces shaped its tail and envelope were under close scrutiny. Some observations revealed that its tail orientation was not perfectly anti-sunward, as classic cometary dust tails tend to be. In several cases, portions of material appeared to deviate from pure solar wind pressure predictions. That suggested complexity in the dust dynamics, perhaps anisotropic outgassing, or jets influencing directionality in ways not captured by simple symmetric models. Spectroscopic traces were equally intriguing. The comet showed richer carbon dioxide content relative to water ice than is typical among comets we know from our own solar system's population. Some analyses inferred a CO2 to H2O ratio far higher than local comet norms. That compositional skew pointed to formation conditions in the parent stellar system that diverge markedly from ours. The molecular signatures, cyanogen, diatomic carbon species, possibly others, allowed estimation of volatile abundances, thermal history, radiation processing, and how deeply the nucleus preserved primordial materials. As sunlight heated volatile ices, the relative rates of sublimation, dust release, and gas drag were interrogated in new detail. Observationally, the sharpest images acquired to date came via the Hubble Space Telescope, which caught the nucleus and compact coma as the comet streaked across stellar backgrounds. From those images, astronomers placed tighter constraints on the size of the solid nucleus. The upper limit is about 3.5 miles, 5.6 kilometers in diameter, though it could be far smaller. The brightness and dust contributions obscure the nucleus itself, complicating direct measurement. In parallel, ground-based telescopes and instruments like the Vera Rubin Observatory and Gemini telescopes provided extended monitoring before and after the Mars encounter, helping refine models of the comet's brightness, evolution, and coma expansion. One of the more dramatic revelations during the Mars flyby was that the comet's tail appeared to grow new features, branches, kinks, and substructures that did not conform to steady-state expectations. These features likely result from episodic outbursts or directional jets of material temporarily altering dust release patterns. Because the Mars spacecraft could sample the comet from slightly different vantage points, they could catch the onset of those features more sharply than Earth-bound observatories would. Thus, the passage past Mars served not only as a close flyby imaging opportunity, but also a dynamic experiment in how an interstellar comet responds to solar heating as it traverses deeper into the inner solar system. Another surprise was that the comet had effectively woken up earlier than expected. Its coma activity had begun at a greater heliocentric distance than comets ordinarily display, indicating that volatile ices in its interior were more volatile or less insulated than typical solar system comets. This early activation implies that its parent environment kept it colder, or less disturbed for longer, preserving superficial ice layers that responded immediately upon exposure to even modest sunlight. That behavior challenged assumptions about where cometary activity turns on. Throughout the Mars flyby period, scientists also attempted to gather time series data, tracking the comet across time to see changes in brightness, coma shape, tail extension, and gas production over hours and days. The interplay of solar radiation pressure, nucleus rotation, jet orientation, and dust dynamics could thus be mapped in unprecedented high-cadence detail. That allowed testing of physical models that link nucleus spin state to jet emergence and how changing illumination angles modulate outgassing. Because the comet was in hyperbolic transit, never to return, these observations were all that would ever be available to us at such proximities. The Mars flyby window was a rare chance to intercept an interstellar visitor at comparatively close range. The geometry of the passage allowed triangulated measurements of position and velocity, refining its orbit and allowing backward integration to constrain its incoming trajectory from the galaxy. Those orbital reconstructions helped narrow down speculation about the region of the Milky Way from which it originated. Though, with caution, galactic dynamical scattering over eons blurs precise origin calculations. Beyond the pure physical parameters, the Mars crossing stirred deeper questions. The fact that an object from beyond our solar system could pass so close to Mars, and yet show such divergence from known comet behavior, meant that cataloging only our local comets gives an incomplete picture. The materials, structural composition, thermal history, layering of ices and dust, and radiation processing that 3I Atlas carried are direct evidence of conditions beyond our solar cradle. The Mars flyby allowed us to sample that evidence up close in a way never before possible for interstellar objects. In one instrumental feather, scientists even attempted to detect faint traces of the comet from the surface of Mars via rover cameras. While that endeavor is extraordinarily challenging due to distance, brightness, interference, and the tiny angular scale, there were reports of stacking images from Mars rovers such as Perseverance's Mastcam Z to find a faint smudge at the predicted comet position. Whether those signals will amount to confirmable detection remains to be seen, but the idea itself underscores how bold the observational ambition became. The passage also pushed the limits of expectation around interstellar object frequency and brightness. Until now, most interstellar visitors were detected only after they became active near the Sun. 3I Atlas was observed while still relatively distant, offering a preview of how sensitive surveys must become to catch more of these objects earlier. Its surprising brightness and activity at distances suggests that many interstellar objects may be detectable long before they enter the inner solar system if we have capable instruments. The Mars flyby underscored that patience and readiness matter. A flyby like this must be anticipated and leveraged before the object passes beyond reach. One more unexpected insight came from its velocity and trajectory. Moving at an enormous speed, on the order of approximately 130,000 miles per hour, or more depending on measurement, relative to the Sun, this comet dwarfs typical solar system comet speeds. That velocity fits with expectations for interstellar origin, but it also presents challenges. High speed means shorter observation windows, greater relativistic corrections, and less margin for positional uncertainty. During the Mars approach, the precise targeting and pointing of instruments had to track fast motion and ensure minimal parallax error. The success of that tracking demonstrated how adaptable spacecraft and telescopes are in pursuing rapidly moving objects. The flyby also tested how well we can integrate multi-platform, multi-angle observations. Data from Earth telescopes, space telescopes, Mars orbiters, and rover stacking were all combined into a coherent interpretation of dust, gas, trajectory, and nuclear behavior. That kind of integrated response has rarely been attempted at this scale for transient visitors. The success, or where difficulties emerged, will refine how missions and observatories coordinate future interstellar object encounters. Importantly, none of the observations showed any evidence of artificial maneuvering or other anomalies contrary to natural cometary physics. Though some speculative voices proposed alien technology or intentional trajectory alterations, the Mars flyby data reinforced that 3I Atlas behaves consistently with a natural body. Outgassing, dust jets, sublimation dynamics, and solar radiation forces. The path through Mars domain didn't reveal sudden course shifts or propulsion-like perturbations beyond what physics would allow for a comet with complex outgassing. Those constraints strengthen the working assumption that it remains a natural object. Still, the very act of passing Mars so closely means that any anomalies, however subtle, could be magnified. If there were asymmetries in mass distribution, internal fracture events, or sudden outgassing bursts, we would have had the chance to detect them in the Mars flyby window. So far, the record suggests a mostly coherent, albeit unusual, object, but the door remains open for surprises in residual data and subtle deviations. One particularly fascinating implication is the question of layered structure inside 3I Atlas. The Mars flyby observations of coma strands and tail substructures allow probing of whether the nucleus is monolithic or a rubble pile, if it has internal fractures or voids, and how heat penetrates from surface layers inward. The timing of release of jets and dust streams, the lag between solar warming and outgassing peaks, and the spatial drift of ejected particles all provide clues to thermal conductivity, porosity, and internal layering. The Mars Vantage added geometry that breaks degeneracies in modeling, refining estimates of how the interior is assembled. Another domain of change involves comparing 3I Atlas's behavior to known comet populations. The flyby highlighted deviations, earlier activity, tail geometry differences, stronger CO2 signals, directional jets, that push the idea that interstellar comets may represent a broader range of structural and compositional diversity than solar system comets supply. The notion that all comets behave about the same is softened. Here is clear evidence that comets from other stellar systems may be more variable, preserving chemical signatures of their birth environments in stronger measure. Because the Mars encounter allowed alternate perspectives, scientists used parallax to refine measurements of the comet's nucleus size, coma thickness, and dust density. The combination of Mars-based and Earth-based observations meant that cross-calibration of brightness and extinction effects could be improved, reducing uncertainties in luminosity corrections and dust cross-sections. Another nuance: the flyby allowed observation of how the comet's tail morphology evolves as it transitions deeper into the Sun's influence. By catching it mid-course past Mars, scientists could anchor models of how the dust tail will stretch, shear, and disperse as solar wind and radiation pressure act over longer distances. That sets initial conditions for how the tail will look back near Earth or toward Jupiter later on, improving predictions and enabling better scheduling of further observations. As 3I Atlas moved beyond Mars and deeper into the inner regions of the solar system, the cascade of data streaming back to Earth continued to challenge established expectations. Even though the flyby window had closed, the aftermath of that event within NASA's control rooms was a surge of analysis, recalibration, and wonder. Every reading from the Mars orbiters and Earth-based telescopes brought forth another layer of questions. This wasn't simply another interstellar wanderer. It was a living record of chemistry, physics, and cosmic history condensed into a single object. The encounter forced scientists to re-examine how the universe transports its ancient building blocks across the vast interstellar medium and delivers them like messages from alien nurseries into our own backyard. The scientific community had been prepared for surprises, but 3I Atlas exceeded all of them. When its reflected light patterns were analyzed, researchers noticed that its rotational light curve was unstable, varying in amplitude over irregular periods. Normally, comets spin in relatively consistent ways, even if slightly chaotic. But 3I Atlas exhibited a precession that made its rotation more like a tumbling motion than a simple spin. That meant the comet's internal structure wasn't rigid. It likely had a low-density, loosely bound composition similar to a cosmic snowball rather than a stone-like asteroid. This tumbling rotation altered how sunlight reached its surface, creating patches of sudden sublimation and abrupt changes in brightness. As each layer heated, gases burst through porous pathways, sending material spraying unevenly into space and reshaping the surrounding coma every few hours. Further study of the light polarization, how sunlight scattered off dust grains, revealed another unusual trait. The reflected polarization angles differed from those typical of solar system comets. This implied that the dust particles within the coma were composed of materials not commonly found in our region of space, or at least that their grain-size distribution was fundamentally distinct. Dust from 3I Atlas seemed to scatter light as if its particles were larger, fluffier, and more porous, suggesting that the environment it formed in had gentler aggregation conditions. Instead of compact silicate grains or metallic inclusions seen in our local comets, 3I Atlas appeared to have fragile, fractal-like dust, the kind that forms in extremely cold, low-pressure molecular clouds. That realization sent a ripple through astrophysics. It meant we were quite possibly witnessing matter born from a completely different stellar nursery, perhaps orbiting a long-dead star or drifting between systems for millions of years before our sun's gravity caught its path. Radio telescopes trained on the comet attempted to detect thermal emissions, a difficult endeavor given the object's small size and distance, but even faint radio signals yielded clues about the abundance of specific gases. Among the most interesting detections were possible traces of ammonia and hydrogen cyanide, both precursors to prebiotic chemistry. The mere presence of these molecules within an interstellar comet hinted that the fundamental ingredients of life may not be confined to any single system. If such compounds can survive interstellar travel, then the raw chemistry of biology could be seeded throughout the galaxy, carried by countless drifting ice-bound fragments. The Mars flyby gave humanity its first practical test of this theory, an opportunity to study how such material behaves in the warmth of another star system's light. The shape of 3I Atlas's coma evolved rapidly after the Mars encounter. Photometric readings suggested periodic brightening every few days, likely caused by jet eruptions triggered by rotational exposure. Each eruption released fine jets that would spiral into faint arcs as the comet rotated, almost like miniature auroras encircling the nucleus. By modeling these periodicities, scientists estimated a rotational period near 9 hours, with secondary modulations that hinted at a tumbling component around a longer axis. This complex motion contributed to a rhythmic breathing effect. The comet appeared to pulse with light, exhaling dust into space in beats of expanding and collapsing luminosity. At the same time, 3I Atlas's path offered a natural experiment in solar radiation dynamics. The dust particles escaping its nucleus were accelerated by sunlight and solar wind, allowing scientists to measure how non-gravitational forces altered its orbit. Deviations as small as a few meters per second could be detected thanks to precise astrometric tracking. These non-gravitational perturbations became a direct measure of outgassing force, the recoil effect of sublimating ices acting like miniature thrusters. The data revealed that the comet's acceleration didn't align perfectly with predictions based on its tail orientation. Instead, it seemed that gas jets erupted from different regions at different times, giving the nucleus an unpredictable wobble. Each variation was another data point about internal heat transport, surface texture, and composition. It was like decoding the heartbeat of a frozen traveler from another world. As the object drifted inward, NASA's infrared observatories picked up an intriguing glow in the near-infrared band, where carbon-bearing ices tend to emit. Spectral deconvolution identified complex organic compounds, likely polycyclic aromatic hydrocarbons or similar large molecules embedded within the comet's dust. These organics are abundant in interstellar clouds, but rarely so clearly preserved in solar system comets, which undergo repeated heating during perihelion passages. 3I Atlas, being on its first and only solar encounter, still carried pristine material that had never been thermally processed. This made its detection a goldmine for astrochemists. Laboratory simulations using collected spectra suggested that some of the dust grains could even contain traces of amino-like molecules or their precursors, shielded within carbon matrices. The idea that interstellar comets could serve as interstellar couriers for organic chemistry suddenly became less abstract and more empirical. As Earth's telescopes continued to follow the comet, the color of its coma shifted subtly from greenish to bluish hues. This was not a trick of optics, but a chemical evolution in progress. The initial green coloration, dominated by diatomic carbon and cyanogen emissions, gradually gave way to blue-tinged emissions from ionized gases. That transition reflected the increasing role of solar ultraviolet radiation as the comet approached the sun. The higher energy photons stripped electrons from neutral gases, producing ion tails that streamed away in direct response to the solar wind's magnetic field. These tails were sinuous, bending and rippling like ribbons as they interacted with fluctuating solar conditions. By tracking their shape and motion, scientists gleaned insights into the real-time dynamics of the solar wind and its influence on dust and plasma behavior at vast distances. Meanwhile, theoretical astrophysicists worked to model the origin of such an object. The energy and trajectory implied that 3I Atlas was ejected from its home system at speeds exceeding a few tens of kilometers per second, requiring either a violent gravitational encounter or instability in a forming planetary system. One possibility was that a giant planet had perturbed it during its early orbit, slinging it outward into galactic space. Over millions or even billions of years, it could have wandered between stars, bombarded by cosmic rays and micrometeoroids, before finally crossing into the sun's gravitational sphere. If that origin were true, then 3I Atlas might be older than our solar system itself. The dust we saw around Mars would be older than any rock on Earth, untouched since before the sun ignited. There was also the question of how its surface retained volatile ices after eons of interstellar exposure. Modeling showed that the outer layers of such a comet should form a protective crust of carbonized material after long exposure to cosmic radiation, effectively insulating the interior. When it entered the solar system and began warming, that crust cracked, allowing sublimation to begin again. That phenomenon explained why the comet woke up so far from the sun. Even minor heating was enough to breach ancient seals, venting gases that had been trapped for geological ages. It was like uncorking a time capsule from another galaxy. Scientists realized they were witnessing a process that bridges cosmic timescales, an interaction between radiation-hardened surfaces and long-dormant chemistry that only stellar proximity could revive. Some of the most remarkable data came from the Mars-based instruments analyzing scattered ultraviolet light. These readings revealed that certain volatiles released from the comet fluoresced intensely in the UV band, hinting at rare species such as carbon monoxide or even exotic hydrocarbons that don't survive long in sunlight. The detection of these transient species suggested that 3Y Atlas carried a chemistry distinct from any comet cataloged so far. For researchers interested in the origin of molecular complexity, this discovery provided a missing piece in the puzzle of how stellar nurseries differ in composition. If its chemistry could be traced back to a specific kind of molecular cloud, we might one day map galactic chemical diversity by following the trails of such visitors. The comet's interaction with the solar wind created a magnetic sheath around its ion tail, a miniature magnetosphere that pulsed and fluctuated as charged particles flowed around it. Mars orbiters equipped with magnetometers recorded subtle disturbances in the local magnetic field as the comet's tail passed within measurable range. These fluctuations gave a sense of how the comet's plasma interacted with interplanetary magnetic structures, creating a natural laboratory for studying space weather on a small scale. Observing these fluctuations near Mars added to humanity's understanding of how solar wind plasma behaves in varying density regimes, knowledge critical for protecting spacecraft and astronauts in future deep space missions. 3. I-Atlas also challenged assumptions about interstellar object frequency. Its detection suggested that our galaxy may be teeming with such wanderers, each carrying a different signature of its parent system. If 3 had been discovered within a few years, the implication was that billions might roam unseen, drifting silently through interstellar space. Our instruments were only now becoming sensitive enough to detect them. The Mars passage showed that coordinated interplanetary observation, using not just Earth but other planetary assets, was essential to capture their fleeting visits. It was an unplanned rehearsal for a future in which humanity could deploy quick response probes to intercept the next one. In the days following the Mars encounter, high-resolution imaging revealed a peculiar asymmetry in the coma, a faint spiral-shaped outflow that hinted at precessing jets. This geometry implied that the nucleus's spin axis was wobbling like a top, possibly due to uneven internal density. A fragment within the nucleus might have been rotating at a slightly different rate than the main body, creating torque that altered its spin. Such internal complexity would mean that 3I Atlas was not a solid chunk, but an agglomeration of loosely held fragments, a rubble pile assembled from different materials. Each component might have originated from a different layer of its parent system, capturing an entire snapshot of that star's protoplanetary disk. During its time near Mars's orbit, the comet's light scattered by dust grains revealed spectral absorption features near the infrared range that matched certain silicate minerals. These silicates showed signs of having formed under relatively warm conditions, implying that not all of 3I Atlas's materials came from the cold outer regions of a star system. It could have incorporated fragments from both hot and cold zones, inner rocky material mixed with outer ices, before being ejected. That hybrid nature distinguished it from many of our comets, which tend to originate from cold Kuiper belt or Oort cloud reservoirs. 3I Atlas appeared to carry the mixed memory of an entire solar system's formation process, preserved in a single drifting shard. While observations continued, models of its thermal evolution were constructed to understand how quickly it was losing mass. Estimates suggested that during its passage near Mars, the comet could have lost thousands of tons of material per hour. This might sound extreme, but for an object of that size, it represented only a thin surface layer. Still, those jets of escaping gas were powerful enough to alter its motion slightly, making precise orbital predictions difficult. As it moved away, small discrepancies began to accumulate in its projected trajectory. These subtle shifts, though minute, fascinated dynamicists because they revealed the power of sublimation-driven motion even at great distances from the Sun. Every new piece of data emphasized how alien yet familiar this visitor was. It behaved according to the physical principles we knew: sublimation, radiation pressure, momentum exchange. But it did so with ingredients and textures that hinted at an entirely different lineage. Its ices, rather than being pure water and carbon dioxide, seemed to include exotic mixtures that didn't match any cataloged volatile ratios. The outgassing rates fluctuated in ways that pointed to a complex layering of materials, some rich in organics, others in refractory dust. Each eruption exposed deeper strata, almost like peeling away layers of a cosmic onion. Through these changes, astronomers reconstructed a narrative of formation that stretched beyond the Sun, across the Gulf of Stars. The data also carried practical implications for future exploration. By comparing how interstellar comets behave with local ones, scientists refined estimates of how frequently such bodies might cross near Earth's orbit. The pattern seen with 3I Atlas suggested that our solar system might be intersected by these travelers more often than assumed, perhaps one every decade detectable with upcoming survey telescopes. This raised the possibility of planning dedicated intercept missions. If we can launch small, agile probes within a few months of detection, we could one day sample material directly from an interstellar object, capturing dust before it dissipates. The Mars flyby thus served as both inspiration and rehearsal. proving that coordination between planetary assets could achieve meaningful science even without physical contact. The comet's passing also illuminated how resilient and dynamic these objects can be. Despite traveling for eons through harsh cosmic radiation and frigid vacuum, 3I Atlas still held volatile gases capable of driving spectacular outbursts. It had survived impacts, cosmic rays, and thermal extremes that would pulverize ordinary rock. Its survival spoke to the protective nature of porous ice structures, which can absorb shocks and dissipate energy efficiently. This durability reinforces theories that icy bodies could transport organic molecules across vast cosmic distances, even surviving the tumultuous entry into other planetary systems. In a way, 3I Atlas embodied the resilience of matter itself, the ability of simple elements to endure across galactic time and distance. When scientists examined its photometric profile in more detail, they found hints that the nucleus might be elongated rather than spherical. Its brightness fluctuated in a pattern suggesting a cigar-shaped or pancake-like form, somewhat reminiscent of Oumuamua but much more active. This elongation, if confirmed, might explain the uneven outgassing jets. Sunlight would strike different surface areas unequally as it spun, amplifying one side's eruptions while suppressing another's. The interplay of shape, spin, and sublimation would then sculpt its path through subtle, continuous feedback, nature's way of writing motion equations in ice and dust. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on 3I Atlas passing Mars unexpectedly? We want to hear from you. Thank you for watching and see you next time.